Thank you very much. Hello, hello. Privyet. So, if you want to find me on Twitter, I know Olga's around. I know she's going to do an amazing sketch for this talk. I'm at the Wizard Lucas. If you want to read some of the crazy things I write, I'm on lucasfcosta.com. And if you've ever thought about moving to London, if you want to work with cool IoT stuff, come talk to me after this talk. We're always looking for good people at Converge. So, this talk is about types, tests, and why flat earthers are bad at QA. And I know this sounds like a puzzling title, right? Because whenever I come to HolyJS, it's always a bit of a crazy topic, a crazy ride. So, don't worry. I'm not here to ask you questions that, don't make any sense, like to ask, for example, why would nature do something as crazy as this? Not going to do that, right? So I'm here to ask more important and more meaningful questions. I'm here to ask you, what do we know about our programs? And I want to ask even broader and more important questions. I want to make this very meaningful, very philosophical. I want to ask you, what do we know, and how can we know it? Because if we can answer these questions about the world, then we can answer them about our programs. And questions related to the nature of knowledge are important, especially in the context of tests, in the context of correctness, because we must know our program to make sure it does what it's supposed to do. So let's think for a bit about how do we get to know the world, right? So in the world, we can learn things through empiricism, right? Through past experience. We look at things that have already happened, and we derive knowledge from them, right? Or we can also get to know the world in advance, through rationalism. We can use logic, right? We have these thoughts in our heads, we have these logical rules, so we just reach conclusions by using deduction, so we don't have to have past experience on a certain subject. So now, if we try to answer how do we get to know our programs, we see that the answer is quite similar. So we either get to know our programs in advance through the use of types, through the use of deduction, so that we encode this kind of knowledge into our program so we can reason about them in advance, right? We can prove properties about them before they even run. And that's why it's called static analysis, right? Or we can also get to know our programs through tests, through experiments, right? We run a test and we see our program behaving in a certain way under certain circumstances, and then we come to the conclusion that, in the future, in similar circumstances, it's going to behave in a similar fashion. So this talk is really as much about programming as it is about epistemology, the branch of philosophy which tries to answer questions like, for example, how do we know what we know? So I think there's a lot we can learn about our programs, about how to reason about them, from the way we reason about the world. And the best way I could find to do this was through an analogy, was through comparing physics and mathematics to tests and types. Because I think that the way physics and mathematics collaborate to human understanding of the world is very similar to the way types and tests collaborate to human understanding of knowledge, of software, sorry. So I think the mathematics is to physics what types are to tests. So starting with physics, the aspect that I would like to focus on is really the scientific method. And there's no way that I can talk about the scientific method without mentioning Bacon. Francis Bacon, okay? So, Francis Bacon is the father of inductivism, which is a way of thinking, a method of reasoning. So in inductivism, basically you observe particular instances of things happening and you generalize. And you take more general conclusions. You observe similar effects and similar causes and generalize, right? So for example, that if you see that whenever you drop something, it falls, well, you generalize that and you say like, oh, the next time I drop something, it will fall, right? So we can make experiments like practical ones, like we can see that this, falls when you throw it. Like, who wants candies? Candies? Okay. See, every time I'm throwing it, right, it just falls. I just come to the conclusion that we will always do the same thing, right? So if you see that the sun has risen yesterday, that it has risen today, you might as well come to the conclusion that it will rise tomorrow. That's what I mean by generalizing. It looks something like this. It's really a bottom-up way of thinking. Right? You do some observations, you look for patterns, then you create a hypothesis, and finally you devise a theory. So in inductivism, now very, very fancy phrase. The premises are viewed as supplying evidence for the truth of conclusion. So the more you observe like the sun rising every day, it might strengthen your belief that the sun will rise tomorrow. Right? The more you see objects falling when you throw them, well, it might strengthen your belief that they will fall the next time. But a very important thing that we should have in mind is that no confirmations of an explanation make it necessarily be true. No matter how many times you see the sun rising, it doesn't mean it will rise tomorrow. No matter how many times you see objects falling, you cannot conclude that they will fall the next time you throw them. You just can't. I mean, you can be quite certain, right? But you cannot achieve truth. You cannot be 100% certain. So this is so important. I'm going to make it bigger. No confirmations of an explanation make it necessarily be true. Bold. Shall we go bold? No confirmations of an explanation make the explanation necessarily be true. Did you get it? Did you get it? Whole slide, maybe. Can we read this together? Can we? Okay, after the tree, I want everyone to just read the slide with me, okay? 1, 2, 3. No confirmations of an explanation make the explanation necessarily be true. Okay, perfect, right? And this is something that, people ended up learning in reality, right? Like, for example, in Europe, when they thought only white swans existed. So, up until the 16th century, people had only seen white swans, and therefore they thought only white swans existed. They thought that every swan they were going to see was going to be white. They were thinking in an inductivist manner. They were taking more general conclusions from particular instances of an event. In London, when something rare occurred, they would say it was a rare bird in lens, and very much like a black swan, because they thought black swans didn't exist, right? This phrase was coined in the 2nd century by a Roman poet, and it was being used in Europe up until the end of the 17th century, up until Dutch explorers in Australia became the first Europeans to see a black swan. And that's just anecdotal evidence of how systems of thought are way more fragile than we think, right? This is the very phrase we've just read, right, that I've just repeated many times. 1 million successful experiments cannot prove a theory correct, but one failed experiment can prove a theory wrong. So then why do we believe that our experiments or tests, right, will prove that our software is correct? In fact, truth is really unattainable. Science is nothing but a successive rejection of falsified theories. We constantly replace those theories by theories that have greater explanatory power. So now let's think a bit about what we do to software, right? We have this mental model in our head. We have this theory about how our software works. We have this idea of how it works. And then we run a couple of tests. We run a couple of experiments. And then we can say, oh, it matches the mental model I have in my head, right? The experiments I've done, I do some observations, I say, oh, it does match the mental model I have. Now, in science, when something goes wrong, well, you cannot really just go and write some code and fix nature, can you, right? But in software, you can adapt the theory you have, right? You can adapt software so that it conforms to your experiments, so that the tests pass. So in the same way that more evidence gets us closer to the truth, more tests get us closer to correct software. We believe really what's most probable, not what's necessarily true, right? When our tests pass, we like to believe, we like to extrapolate and generalize and say oh yeah, my software is working. But is it really? Is it? So blindly trusting science is dangerous, but so is not trusting it at all. In the same way that blindly trusting tests is dangerous, but so is not writing any tests. So science is not dogmatic, right? If you're contesting something, if you have contradicting evidence, right, it will accept your contradicting evidence. It will look for evidence to disprove its theories. In the same way that tests are not permanent. As I've just said, when you have this theory in your head about how your software works, you can adapt it to conform to your experiments. You can adapt reality. So perhaps we could learn a bit about how to write good tests if we think about how we do proper science. So basically what we have here is the hypothetical deductive method. It basically consists of forming a conjecture, stating an explanation. You have having this mental model in your head. than making predictions, right? So you think reality behaves in a certain way, you have predictions, you do some experiments, and you see whether they're going to match the model you have in your head, right? So you're going to observe if your theory matches realities. And this is pretty similar to the way we write tests, right? We have this idea of how our software works. We have predictions, which are nothing but what we encode into tests. Right? When we write tests and we expect something to be something, there are our predictions. And when we run the test, we're just running an experiment. We're observing whether our theory or software matches reality. And a very important thing here is to be willing to be wrong, right? You need to have assertions which you don't know whether they're going to pass or not. They need to be falsifiable, right? You need to be able to prove yourself wrong. That's the whole point. Your observations should not strive for confirmation before this confirmation, because if you try to prove yourself right, you eventually can. And your tests, they must be risky. They need to be able to falsify your theory, otherwise they're worth nothing. In other words, if it never fails, it's useless. Right? In the same way that if a scientific theory can't be refuted, it's useless. And a misconception that many people have is that science is trying to prove something, and they say like it's been scientifically proven, but actually science disproves, and pseudoscience tries to prove. Pseudoscience tries to look for confirming evidence, tries to ignore everything that contradicts their beliefs, and just chooses to believe something just for the sake of believing in it. And in the same way that physicists cannot prove they're right with experiments, tests can prove that our assumptions about our code are right. We can only be proven wrong. Right, so now let's talk a bit about functions, right? Let's make this a bit more tangible. So let's say we have this function which has two tests. We're passing it two different inputs, and we're getting two different outputs, right? So these tests are the green crosses there. And while we're testing it, we're passing an output, we're getting the right output. Everything seems fine. Now, we can have a function which produces the exact same output for the exact same input, and is not the function that we want. So we need to add tests which are going to rule out those intersecting implementations, right? That's what we're trying to do when we write tests. Because tests can prove that we're correct, tests can only prove that we aren't. Tests just provide evidence, and the more evidence we have, right, the stronger can our theory be. Right? It's about contingency, it's about having more evidence. In the same way that experiments do, right? Which is why we must watch out for confirmation bias. As I said, if you try to prove yourself right, you will be able to, and you should not. You should try to disprove yourself. Because otherwise you might ignore failing cases, or you might design things to suit your beliefs. Which is why I don't think flat earthers are good at QA, because they're trying to prove themselves right. They ignore all the contradicting evidence. Like if they were writing tests, they would not do the right assertions. They would ignore the failing tests. They would try to prove that the software works. And this is not the kind of behavior we want from a QA. So flat earthers are not good scientists. And people that are not good scientists cannot be good testers, right? If you're a good scientist, you're a good tester, right? The ways of writing tests and the ways of doing science are very similar. And I don't know, maybe like if anyone needs a tinfoil hat, I have one. So, don't be scared to ask for it. And really, basically, they ignore observation that's very important. And experiments depend on that observation, because observation is what is going to tell us whether our expectations match reality or not. And when it comes to tests, observation really matches to assertions, right? A test which does not contain assertions simply checks if the code can run. And, it's good that your code can run, but is it correct? Right? Assertions are the way we encode our predictions in tests. And, observing is a very subjective commandment, right? So Karl Popper had this thing where he was in a class and he told people, observe. And everyone observed a different thing. And this is one of the ways that science can be biased. Because observation is always selective. It needs a chosen object, a definite task. It presupposes similarity and classification, which, in their turn, presupposes interests, points of views, and problems. So science is not only biased in the kinds of projects we choose to fund, but also in the observations we try to make, right? So it's important to think about what we want to observe, what will contradict or not our beliefs, what matters or not. So this just proves that, really, code coverage is not really a good measure for correctness, right? Code coverage is useful in different ways as a metric, not really an absolute metric, but to see like what you're missing when you're testing, right? To see which lines you're not covering so that you can go and cover it. But if you don't have any assertions, if you're not making the right observations, if you don't know what to observe, your tests are useless. And that's if you believe in code coverage, okay? Because, you know, James O'Coplin said something very interesting. He said, I define 100% coverage as having examined all possible combinations of all possible paths through all methods of a class, having reproduced every possible configuration of data bits accessible to those methods at every machine language instruction along the paths of execution. Right? So really, you would need to test all the way down. Like, you need to test the compiler, you need to test the operating system, everything, if you want to have really 100% code coverage. And this now is very strong. Anything else is a heuristic about which absolutely no formal claim of correctness can be made. If you have 100% coverage, you cannot say, oh, I'm covering everything, my software works. Because you cannot prove your code works, you can only prove it doesn't. At least not with tests, right? Think about how many different kinds of tests you would have to go through every single point to rule out all the possible intersecting implementations, right? So what do we do when tests are not enough, right? Is there any hope left? Well, now's the time that I talk a bit about types and about mathematics, because I think those things, they're very related. Because in mathematics, we can achieve truth, right? We have this very constrained system with a bunch of rules, a bunch of axioms, which can allow us to reach mathematical truth, certainty. So in mathematics, how do we achieve truth, right? So we have a conjecture, which is something that we believe it's true. And then we go on and we have a proof for it, right? We follow very rigorous mathematical reasoning to demonstrate that that statement is true. And once it's proven, all it needs to do is indeed follow all the rules, right? Be correct within all that constrained system of logic so that it can be truth. In a certain way, all mathematical proof is tautological, right? Because it's kind of obvious, because it's follow the rules and it gets somewhere. And that's a series of steps that you take. And that's because mathematics is not a science, right? Very Instagrammable slide, I know. Mathematics is not a science from our point of view, in the sense that it's not a natural science. The test of validity for mathematics is not experiment. We don't need to have past experience. We don't need to have past experience to prove that something is correct in mathematics, which is why they're related to types. Because we can prove properties about our programs before they even run. We can reason about them in advance, right? Types allow us to abstract reality in a certain way so that we can prove things, right? So they can get to truth within that constrained system of rules within our type system. So really this is kind of like David Hume's relations of ideas and matter of facts, which is the difference between when you devise knowledge before it actually happens, a priori, if you can use deduction, or if you have to have experience, when you can devise knowledge a posteriori. So why does physics rely on mathematics? Well, because of the power of abstraction. Because it can abstract away all the imperfections, all the irrelevant details in nature, right? So that it can encode it in a formal system that we can easily reason about, right? So when we have abstraction, we're not anymore concerned about particular instances of inputs going to particular instances of outputs, right? We zoom out a bit, and we only think about types. We only think about what maps to what. So now we don't see particular instances of strings going to particular instances of integers anymore. Right? We see categories, we see transformations. So we basically zoom out, we ignore all irrelevant detail. This is really the end of the road for abstraction. You cannot abstract more than this, and this is how we reason about our programs. And because we have this set of rules which are very well defined, we can think about things in advance, right? There are properties we can devise from this system, like, for example, from the fact that you have something like a function f which takes you from A to B, and a function g that takes you from B to C, and therefore you conclude that function h, which is a composition between g and f, will take you from A to C. So this is how we reason about our programs, right? This is the very magic of computation, is encoding things into symbols that we have clear rules to manipulate. And this is, in a certain way, Leibniz's dream. Right? Leibniz wanted to have this system of computation in which he could solve everyone's problems by using exact logic, right? By just encoding things into a formal system that you could use to reason about the world. He said that if controversies were to arise, there would be no more need of disputation between true philosophers than between true calculators. For it would suffice for them to take their pencils in their hands and to sit down in the abacus and to say at each other, calculemus. This was his dream, right? And so now you might be thinking, okay, so why don't we just use mathematics, right? You just solve the problem. Come on, Nobel Prize, right? I mean, do you have any Nobel Prize winners in the audience? Nice, we have 2 today. Amazing. But well, it's not really possible, right? Because this guy. So this guy said that if a logical system is consistent, it cannot be complete. There will be true statements which won't be able to be proven. And there's also no way to show that any useful formal system is free of false statements. You know, Kurt Gödel. Well, now getting a bit less philosophical. So how can we constrain the implementation of a function in such a way that we only have one possible correct implementation? In other words, how can we rule out all the incompatible implementations, all the implementations that are not the ones we want? I know you've been dying, like you've been waiting for this moment where I show a very simple formula until now. Well, this is so simple. So basically, we need to think about what is the number of allowed implementations. Well, a number of allowed implementations is the total possible implementations of a function, the number of all the ways you can implement a function, minus the implementation invalidated by tests. And there's a great talk about this in which a guy goes really way deeper into the subject. Julian Truffaut, great talk at Lambda London. I highly recommend. The links are down there, by the way. So he came up with this idea of a number of allowed implementations. So we can be sure that our functioning is correct when the number of allowed implementations for a function is only 1, right? If there's only one allowed function, guess what? Is what we want, right? So basically, he called this a valid implementation count, right? So smaller VICs, smaller valid implementation counts means the functions are more constrained. So when we only have one valid implementation, well, there can only really be one possible implementation, right? The correct one. So now, covering every possible output is feasible. It was not, right? Going to every single point in that function was not. So through a combination of experiments, through a combination of tests, and logical constraints, we can achieve more certainty. So let's think for a bit about how this function maps from string to string and all the number of possible implementations which are allowed here. Right? So if we map from string to string, there's so many different functions that we can have. Now, if we limit it, right? Let's say we do something very simple, just use types, right? So we now limit that to having a limited number of countries and a limited number of continents. So now it's way more feasible just to go through every point. Now, there's still a lot of valid implementations, 7 to the power of 195. I know it's a lot. But I mean, you can enumerate that, right? And that's just because we had a type. So for every input tested, we reduce the number of possible implementations 7-fold. So now if we write a test for it, all those 7 possible outputs are going to be collapsed into 1. Because now we wrote that test, we're passing an output. Now it can't be those 7 outputs anymore. It will only be 1 because we returned a test for it. So now, every time we do it, we reduce it 7-fold, and therefore if we test 195 times, guess what? We have 1 possible valid implementation. Right? So through this combination of using types to constrain our functions enough, we can achieve more certainty. We can test a finite set of possible inputs and possible outputs. So type systems really allow us to constrain reality in such a way that testing all possible inputs becomes possible. And this is really very similar to making impossible states impossible. So there are great talks about this. My friend Farzad, I've seen many talks mentioning this today. And it's such an amazing idea. Farzad's talk was great. So, just go on YouTube and watch his. Very practical device. So here, basically, my examples are a lot more basic than that. So basically, we can leverage correctness with type by making these impossible states impossible. And just as an example, I've chosen the only card game I know how to play, Blackjack, because of this movie. Has anyone seen it? Just don't. It's horrible, really. I didn't really learn a lot, so I still had to Google it. So, well, anyway, now I'm going to teach you to play Blackjack and to also constrain your programs using types, right? So in Blackjack, we have players which have some contact information, and because this is very important. I mean, Blackjack is a very important game. You want to know who you're playing with, right? So these people can have emails, can have country codes and phones, right? But there's problems there here, right? We can have people that have a country code but no phone, or a phone with no country code. We can have a player which only has a name. So if we basically just encode our phone type into itself, right? Basically, we can have a country code and a phone within the phone type, and now we can use that as the type for a phone. So now we cannot have anymore someone with a phone which doesn't have a country code and a phone, but we can still have someone that doesn't have neither an email nor a phone, right? So now if we encode that into a contact information, that's not possible anymore. Now, going forward, we can still have a player which has invalid cards, right? I don't think anyone here has seen a -2 in a deck, have they? I mean, if you've seen, you must have lost some money, right? So we can still have invalid cards. So we can do something very simple. We can just have a union type with only the valid cards, right? But now we have another problem, which is that we can still only have one card. And in Blackjack, you must have at least 2 or more cards. I didn't know this. Learned this in my Google search. So how do we do this? Well, we can just have a type, 2 or more, which takes t. And now we'll only be able to have in our cards a hand, which needs to be an array with 2 or more items. But now, in our game, we can still have a lot of invalid states, right? We can have 0 players. Wrong. We can have a win state with an X player. We can have a running state with a winner. We can have a tie with no tie players. And if people are tied, we need to know who's there, right? So now, if we encode these states into their own types, right, we're able to do things like making sure that the win state will have a winner, making sure that the tie state will have 2 or more players which are in a tie. So we're just reusing our types to make it in such a way that our game will not be able to have invalid states anymore. However, in our unfinished state, as you can see there, we can still have an X player, which is not playing. So now we can also encode our playing states, right, into types, and we can have a player state, which can be either a playing player, which is a player state, which is in a playing state, or a non-playing player, which is a player in a non-playing state. Now, we can only have valid players. Right? And we can go on and do this and, really cover everything there is in Blackjack, but it's way more complicated than I thought, so I don't think we have time for that in an hour. We can go from the most complex to the most simple problems, right? The very problem that all languages are typed and some will tell you when things could go wrong and others won't, that's a problem itself, right? If you've seen an uncaught type error in JavaScript, you're talking about JavaScript, it's typed, it just won't tell you before it just explodes, which is very frustrating. It goes much beyond just prohibiting invalid properties, right? Avoiding combinatorial explosions when you have React components, or just doing exhaustive checks to make sure that you're handling all the actions in Redux, for example, like in this case where we're not handling a known. And you can model uncertainty in many different ways. So basically what I'm trying to show here is that you can model reality in such a way as to make things easier, more constrained, right? So that your experiments are going to be easier to make. Because producing reliable software depends on choosing good abstractions and having the correct experience. You cannot only rely on one or the other, right? You need to have both. So let's talk a bit about how we can leverage correctness with tests, right? Because, automated crap is still crap. Just writing tests. I mean, come on, we all know this, right? I mean, who here has written so many tests and still had their programs fail? See? You cannot prove that you're correct with tests, as we've seen. So the first thing I would like to talk about is coupling and cost management. Because I think it's important to understand what matters in software so that we can, write software that matters, right? And, I think we should start this with a class I'm going to call Capitalism 101. And this class is about things that matter and things that don't in our current economical system, okay? So apparently what matters is less cost and more revenue. Now, can you guess what doesn't matter? Code coverage, correctness, tests, right? So if your software is making, so let's say you had a software which is making a whole lot of money, right? Really like a lot of money, right? But it has 0 tests. does it really matter? So, I mean, it might matter for you who's having to maintain it, but, for the people that actually own it, I don't think it does. And the truth is that tests do add some upfront cost, right? Because you spend some time writing them. So you need to pay that cost, right? But the thing is that it reduces long-term costs. Tests are really an investment, right? You get paid back in installments, right? You get paid back in small chunks. So basically, when you write tests, you're writing it as, a gift for your future self. It's kind of like documentation in a certain way. And tests are also subject to diminishing returns. So when you write a lot of tests, you start getting less and less value out of them. So you should strive for a balance between how much time you spend writing it, because in the end, time is money, and how much value you get out of it. Because something that many people don't say is that you do pay for tests and maintenance, right? These tests have a cost. They are code too. You have to maintain them when you change code, and that adds time. Hopefully, because you write good tests, those tests will make refactoring easier, safer. They will reduce the time you need to spend testing it, right? They will reduce the number of defects you have in production, and therefore they'll generate more revenue. This is why we write tests, right? We don't write tests because, we're programmers, we like correctness. We write tests because it produces money, right? That's why we do it. So in order to make these easier to maintain, it's good to avoid coupling, because the more tests you have to change when you do it, when you do a change, the bigger your cost is. So now when people ask me, okay, but how fragile should they be? How much should I avoid coupling? Well, the answer is very subjective. My advice is always to think about when you would like them to break. And now there's people that say that tests should never be coupled to implementation. And the word never, it's not always a good word, because everything has nuances to it. So if you're testing something, right, and you couple it to the implementation, but because certain implementation details are important to the way you do it, it's fine, because whenever you change your code, you're going to be conscious that you're doing that change, right? So you're going to be like, okay, so my test is failing, even though the code is still correct, but you're now conscious that you had to make that change. So I like to avoid coupling, but I think it's smart to avoid coupling when you can, when it matters, right? And you also should make sure that they fail, because if you try to avoid coupling in such a way that your tests will never fail, they're going to be useless. They won't produce any information. And tests that never fail, they're not scientific. They are pseudoscience. So now that we've talked a bit about value, let's talk about different kinds of tests and the different kinds of values they provide. And we do need to talk about test-driven development. This is the kind of chat we had to have. Because, let me say this, test-driven development is not about tests. It is not, right? I mean, someone might argue, then it's not a good name. Yeah, I know. Maybe it's not. But it's what we have. So TDD is about taking small steps, right? If you read TDD by example, you see that, unit tests, they're not really that much used for correctness. I mean, they are, but not that much. What Ken Beck is trying to show is how to use unit tests to step through your development process. Have you ever had the necessity of doing a git checkout dot, of resetting every single change that you had in your machine because you didn't know where you are anymore, right? That's what happens when you take steps that are too big, you get lost. So basically, TDD is a fear reduction tool. The more confident you have, the bigger are the steps you take. The bigger are the chunks of code you write, the bigger are the tests you write. So basically, you can write very small tests that always will fail in certain circumstances. You can hard code some answers, and you can step through very slowly. This is what test-driven development is about. I've written about it before. I've got a blog post about it. So it's on lucasfcos.com. Go there, read it. Very nice. And that's because different types of tests generate different kinds of value, right? Unit tests, they're cheap, they're fast, and they produce relatively low value as well. But they're a good tool for iterating. And now, you might say, well, can I really tell this difference? Is it really easy to tell tests apart? Short answer is no. But the long answer is that, well, even though you're not going to be writing tests, you're going to be like, oh, this is like the topmost level in my testing pyramid, know a lot about tests. It's not how you do it, right? It's good for you to know that, so you know what kind of value they generate. So basically, when you're doing unit tests, you're aware that they're cheap, But they generate value when you're iterating. When you do integration tests, well, they're more coupled in a certain way. They're going to fail more often, but the thing is they produce different kinds of guarantees. They're going to guarantee your functional requirements work in a certain way. Or when you do like end-to-end tests so that you can guarantee that things work from a user's point of view. So you must really talk about when to write what. And this is, of course, very subjective advice because people write different kinds of tests in different kinds of situations. But I think there is some advice that can be productive for when we write code. And this I think, is very practical advice. So when should you write unit tests? Well, I'd say you should write unit tests in parallel with writing code for doing TDD, right? Not as... So basically, it also helps you refactor and also helps you step through the code. So you have small steps and you can do it iteratively. So they help you guide development and help refactoring code safely. And you should now use them mainly for correctness, but also as a documentation for your future self. You can read some tests and you can know like, oh, this interface does this, it behaves in a certain way. It's in a certain way documentation of how a certain module, a certain piece of code works, right? Your future self will thank you. So now, people might think it's weird, why did you put snapshot tests in their own category? Well, because I don't use really snapshot tests when I'm iterating that much, but as a guarantee for my future self. You remember the thing I told you about when you want tests to break? Because in a certain way, snapshot tests are going to create a certain kind of coupling, right? If you have this huge snapshot of markup, if anything changes, things are going to break. But the thing is, you're now conscient. You now have this, you have to change the test. You're aware that it has broken, right? So you should also do it when asserting on output is repetitive. How many times have you written some code which produces a huge chunk of output, and you're like, oh, now I have to copy all this thing and put it on my test. And then the next time, you just want to do that same thing again, but you're just doing that so that you're aware of when it changes, right? It's good for when your output is too big and too detailed to manage. Like, for example, Jest. Right? So Jest uses Jest to test itself, and it does it by using snapshots. So if you go to Jest repo on GitHub right now, and you go to a folder called end-to-end, you can see how Jest tests itself. And basically, the way Jest tests itself is by using snapshots of the console output it produces. Right? So you know what you see in the console when you run Jest tests, the summary in the end, the list of tests that have run, the failures that you've got, where the problems are, and everything. The way Jest tests that, because Jest needs to guarantee it works from the user's point of view. Right? Jest has unit tests and also needs to have unit tests. Is by taking a snapshot of that, and then it checks different parts of that snapshot to see if things have worked. So basically, if you want to check in Jest, for example, that your summary will display the correct number of tests failing when you run the test. What you're going to do, if you're writing code for Jest, right, if you're contributing to Jest, is you're going to write a test, like if you were in Jest, which has a few tests failing and a few tests passing, and then you're going to use Jest to run it. And it's going to generate some output, which you take a snapshot of, and then you compare that snapshot with the snapshot that's correct. Because console output is too big and too detailed to manage. So when you update Jest, right, your end-to-end tests are going to break. Then you can go on, take a new snapshot, see if that matches what you want to see in the console, and that's how Jest tests itself. So a few tips for snapshot tests is finding relevant serializers, because you're going to have to maintain these things. And if you're going to have to maintain something, oh, it better be readable, right? So Jest, for example, uses Jest snapshot serializer raw to make sure that the output is going to be more readable. So they're going to remove lots of spaces, lots of unnecessary characters when you want to see just a summary, just what tests have run or what tests have not. They even have an interactive mode so that you can update snapshots quickly and iterate to them very quickly. Because when you do snapshots, you don't want to be reading them like, taking a lot of time to notice what has changed. You want to do it to be aware of the changes that you're making. And something that I also see many people doing is using snapshots for everything. But that creates a lot of coupling, and I think you should only use snapshots when it actually matters, as we're going to see in a bit. So you can also use custom, what they call asymmetric snapshot matchers to balance maintainability and rigorousness, right? Because when you take a snapshot, because you have so many detailed output, maybe you want something, maybe something's not deterministic, right? Maybe you have a random number. So you can just expect your snapshot to have a number there. It doesn't need to be a specific number. So remember when we talked about costs? Basically, this is where it comes into play. So if your snapshots are very costful to manage, you can use these asymmetric matchers so that you can have some more maintainability, so that you don't have to be changing it all the time. Right? In this example, for example, what a good phrase, isn't it? You expect a person to match a certain snapshot, so you expect its name to have a string matching a certain regular expression, or you expect pets to be a certain array containing a certain item, so that you don't have to be really updating that snapshot all the time. And don't be afraid to use partial snapshots, right? Don't use snapshots for everything. You can use snapshots for example, big chunks of markup, big and very detailed output, and you can use assertions for what actually matters, right? If you have some piece of logic which you just need to test the result, well, you can just assert on that result. Now, integration tests. When should you write integration tests? To test functional requirements, to ensure correctness. This is where correctness comes more into play than actually iterating through code. To ensure that you're using third parties' dependencies correctly, or to ensure you're interacting with libraries in a certain way. When certain behavior is critical to your application, right? If it's important for you to call a certain integration, well, you might be checking whether you're sending that HTTP request that you need or not. And things that I consider integration tests that, this line is a bit fuzzy. So, for example, when I talk about here interacting with actual components, I'm talking about really seeing if you're using React in the correct way, right? Because you want to actually see if the library is doing what it's doing. You want to render something, you want to interact with that component in a certain way, and seeing if the right output is generated. Seeing if it will update when the things you want change. When you want to, for example, send actual HTTP requests. When you want to hit a database and fetch data from it, right? Let's say you have an API and want to test it. So you can send actual requests. You can see whether the data is really being saved in the database in the right format. And then you can query it, and you can see whether the results were saved correctly. When you want a certain IO, when you want to make sure certain files were saved or not, or when you want, for example, spin a separate process to do a separate thing. So you can just spin the process, see if its output was correct. Now, end-to-end tests. Well, end-to-end tests are useful when interaction with a real UI matters. And this is more for example, when you want to have guarantees that your users are going to be seeing the right thing. When you want to ensure that these services work from their perspective, right? So these are the most valuable kinds of tests when it comes to correctness. And I really can't emphasize how good this thing is, really. And it's not because I have friends that work at Cypress. I was also reluctant before I tried it for the first time, but it just works so nicely. I was using Selenium before that, and Selenium is a bit painful. Does anyone use Selenium here? Isn't it a bit painful? Well, it's a bit slow sometimes. It's a bit hard to set up. If you want to isolate everything, just setting up everything is a bit annoying, but Cypress just makes it so nice to set up, so easy to set up. They have amazing docs. It's so easy to access your application's environment. So you're just testing what matters in each test. It's also not flaky, which is a big deal, because Selenium is very flaky. You have to have awaits all the time. And the way they do this is by using a global chain of events. So basically, instead of having promises, you just send events to a queue, and that queue is going to be executed sequentially, and you can have waits. Basically, it's very nice. It's a bit weird in the beginning, because you're like, oh yeah, I'm just going to wait on this, because it must be a promise. But actually, it's not. But it's the way it was designed, and it simply works. Really, really good. Highly recommend if you're thinking about doing end-to-end tests. So avoiding false positives is also important, right? Because if your tests are passing and they shouldn't, well, then, our test is going to fail in production. That's not very nice, is it? So one of the things you can do to avoid false positives is avoid loose assertions. So loose assertions, right? Assertions that are loose by design are assertions that allow multiple results to pass. Let's say, for example, that you're expecting something to be defined. How many things in JavaScript are defined? How many things are going to pass tests that have this assertion? Many things. So you want to make your tests as constrained as possible so that they fail when it matters for them to fail. When you expect, for example, result to be a number, how many numbers can we have? Well, a whole lot of numbers. But you know what else passes into this test when you expect something to be a number? Not a number. Nice, isn't it? So another thing that is also considered loose expression is when you use not. And that's why I recommend people to not use not when they do assertions, right? Not is tolerable in certain cases, but only if you need to assert that a specific event didn't ever happen. In every other case, it's just a loose assertion, right? Because when you expect a certain result, for example, to not be 1, it can range from 1 to plus infinite to 1 to minus infinity, and this is really just, infinity. So these are loose assertions. Loose assertions are things that allow multiple outputs to pass, like when you have an OR, right? So if you're expecting something to be 1 or 2, you're expecting multiple outputs to happen. And this is why you don't see ORs in assertion libraries. And this has been requested many times, right? I maintain Chai, and many times I've seen people requesting OR in assertions. But OR is not really the way to go, because even though we have loose assertions, these loose assertions, they're in a certain way, it's implicit on them. And we have warnings in our docs saying like, please, if you can, try to avoid using this. They're useful in certain cases, as we're going to see in a bit. But OR explicitly encourages bad practices, which is why we have never included it. It's also useful to assert on a certain subject at a time, because it makes tests more readable, it makes them more understandable. Let's say you're expecting, for example, right, a function which I call result, to not throw a certain error, right, a type error with a certain message. Should this fail if both don't match, or should it fail if only one doesn't match? Right? This is a semantic question. Right? If you have a not in a chain, right? It's like when you're writing. If you have a not somewhere in your phrase, should it negate everything that comes after it? Should it only negate the assertion that comes right after? This is more a semantic question, right? Which is why, if you try to avoid asserting on multiple subjects at a time, your tests become more readable. Another important thing is to avoid tautological tests. And I know we talked a lot about coupling. And basically what tautological tests are is using your software to test your software. Right? So in this example, what I'm using is using a cat factory to test a blue cat factory. And I'm using my code to test my own code. So if I change my code, my test will never fail, and that test never produces information. So it's good to use your code to test your code in certain ways, but only when you have the guarantee that the other part that you're using works. Right? Because otherwise, you're testing something against itself, and it really doesn't make any sense, because changing it, even though it will make it fail, will still make the test pass. So it's important to have, as well, meaningful feedback, so you know what to fix quickly, right? Because what we're talking about here is time, and time is money. And what's important in software, if you remember, is generating revenue and reducing costs, right? So for you to get meaningful feedback, you need to choose the right assertions, right? Because different kinds of assertions will generate different kinds of outputs, which will make errors more readable. And the way assertion libraries do this is by using something that's called an assertion error. So when you see, Jest throwing an error or Mocha throwing an error, basically what is happening is the assertions that are within our test, they're throwing errors. It's not just the Jest runner, the outside layer of it. So these assertion libraries, they're going to take a certain result, they're going to compare it with another thing, and they're going to produce an assertion error. And then Jest, for example, has another library to produce a diff. And you can use this. Jest is very nicely divided in many packages. So if you go to Jest repo, you can use Jest diff, for example, to see diffs between objects, which is very useful when you're debugging something. For example, even if you're not using Jest and you want a better diff, you can just download Jest diff and use it to compare objects. And also, another thing that assertion libraries do, which is very, very helpful when you're debugging tests, is hiding certain parts of your stack trace. Right? And the way they do this is very interesting. Because since we're just dealing with assertion errors, there are many properties of errors that we can manipulate to give you more meaningful output. So in this example, we have a function A calling function B, which calls function C. So we capture the stack trace into my object here using error.capture stack trace. And now if we log the stack trace that we stored on my object, we'll see that the call that we have here, where we store the stack trace on B, is the call that appears on the top of the stack. So now, if we pass it a function to capture stack trace, we'll be able to hide certain parts of the stack. And therefore, we can hide our own implementation. Right? So now let's see we have A, B, C, and D calling each other. And we, on D, capture stack trace passing B. What happens when we log it is that we only get frames that come after, before B in the stack. And this is how Chai hides certain parts of stack traces to make errors more meaningful. So if you look at this assertion, you'll see that whatever is inside expect is what's going to happen first. And everything else is going to be within Chai. So would you like for you, when you get an error, to see all the huge stack trace of like Chai calling itself multiple times in multiple places? No, because it's not useful for debugging. It just generates information that's not useful, right? So when you create an assertion, the thing that's inside of it will run first, right? Because it's what's within expect. And basically, we wrap that into an assertion object. And now every property that you access within your assertion is going to trigger, for example, a getter when you access to, and it's going to keep running functions and returning that assertion. So every time you run a function within Chai, right? We're going to capture that stack trace, and we're going to remove every frame that's below it, so you only get the meaningful output, right? When you access the D property, for example, right, we're going to be setting a flag into the assertion object that we're returning, so that we can use that in future assertions, right? And also, by the way, remember when we talked about semantics, about whether flags should be valid for everything that comes after them or not? Well, the deep flag, it cannot be unset in the same way that not can't. So, do one assertion at a time. This is another factor why it's important to do one assertion at a time. And also, feel free to create your own assertions, create your own plugins. Try has very nice documentation for this, for you to add assertions that are either properties or methods or chainable methods, and it's really easy to extend. So, when you have a task which is very long, when you're just like sorting a bunch of things, like preparing your input in a certain way or not, well, you're repeating that into every test. Well, that adds cost, right? Because you need to be maintaining that, it's repetitive, it's annoying. So you can just write a plugin which does that for you. And not only Chai allows that, Jest also allows that. Jest expect library also has this extend method, which you can use to extend it and create your own assertions. There's also Jest extended if you're using Jest. Very good, so you can get more assertions that are more meaningful, make your test more readable, and produce better output. Another thing that's important is to isolate external dependencies, right? And when I talk about this, I talk about mocking. And then I usually get this question, which is, when should I mock things? Well, the easy answer is, well, just mock everything that you don't own. The hard answer is that you should mock whatever is not yours, right? And this is especially valid, for example, when you have like DOM APIs, right? You don't want to see if the DOM API is working, you can just trust it, or you don't want to test other people's libraries. What you want to really test is whether your code is doing the correct thing, right? So I think I'm going to have to speed up a bit because I have 5 minutes. But anyway, you should mock things and be conscious of what value it's going to generate, right? Because when you mock things, your tests get more distant from reality, but they also fail less, right? So there's this cost between the value it provides by failing and the value you get by not having that much work to maintain. So also, what do I mean by trusting browser APIs? So by trusting browser APIs, I mean just stub functions that are important for you to call in DOM, in JS DOM. For example, if you need to make sure that you're calling a certain function which is in a window, for example, you can just stub it, and you can just see if it's being called. You don't need to test whether it actually works, right? And this is because you have transitive guarantees. So by transitive guarantees, I mean not having to test everything because you have tested the pieces of it, right? So if you have a unit under test which uses module B and module C, well, you don't need to be testing the output all the way passing to module B and module C. Because if you have tested every individual part, you can only test if that part is being called. And because the other part is already tested, well, you can conclude, therefore, that it works. But you should be careful, because that makes tests more distant from reality and makes it harder for them to really fail when it's meaningful. So there's a bunch of tools for you to mock. I won't go into this huge table now. But these slides are going to be online, by the way, so you can just go to SpeakerDeck. I'm going to put them there, tweet the link after. And basically, my advice for you is, try to be conscious about what you mock, thinking about value. Really, not just thinking about, I'm just going to mock this because it's going to be pretty, it's going to be more isolated, and I'm going to write this whole bunch of tests, because tests provide diminishing returns. And now finally, eliminating nondeterminism matters, because if you remember what we talked about functions, well, that's only valid if they're deterministic. Because semantically speaking, flaky tests are the same as failing tests. And flaky tests decrease your confidence in build. And flaky tests don't allow you to differentiate flaky application code or flaky test code. And there's a few ways to solve this problem. The approach one is to mock out the non-deterministic pieces, mock out timers, mock out things that are not deterministic so that you can make them deterministic. The other thing that you can do, which is the second way of solving problems, is to ignore them, which is to take variability into account. So use assertions that are loose. That's why we have loose assertions, right? Because sometimes you want to take that variability into account. Use assertions that allow multiple outputs to pass. And the third approach is to make the code actually deterministic, to solve it on the code side, not on the test side. And finally, another thing that you should be careful of is making your tests run fast. Because if they don't run fast, you're not going to run them often enough. And not running tests often enough decrease the kind of value they generate. Because if your tests are slow, they don't get run frequently, as I've just said. So quick feedback encourages you to run them quicker, encourages you to take smaller steps to iterate in a more gradual fashion. And it also decreases frustration and creates a more positive feedback loop. So really, what we should do is be very careful about what we test. You know, automated crap is still crap, and we need to think about the guarantees we have and why we have them and how they collaborate to the way we understand software. Because good tests, they cue flawed theories, and they allow us to remain alive to guess again. And that's pretty much it. So write code, read books. Thank you.
Hello, Lucas.
Thank you.
We have 2 minutes, so I'll have many questions and quick answers. Now, first of all, there are so many different kinds of testing, right? So, you know, when I was studying computer science, we had to deal all kind of sanity testing and monkey testing and regression testing and smoke testing and all of that. So, if we take an example, like let's say you have a legacy project and it doesn't have any tests, it has really kind of crappy code base and all, and you want to bring it to a slightly better foundation testing-wise, where would you even start? What would be your strategy?
So I would.
And so sorry to interrupt you. And what kind of tests would you start with first?
Okay, so I would definitely start by using small unit tests to iterate through the code because, you know, when I go to change a piece of code, I can start there, I can test that very small piece. You know, it's kind of like when you try to do big changes at once, like big bang deployments, you know, that usually doesn't work. It's like full rewrites, right? I don't believe in full rewrites. You know, you should do things gradually. So what I would recommend is to go to the legacy project and write tests for the bits that you're changing. Because as you go, you're going to change different parts of the code and you're going to start having tests for it. So that would be my advice. And
then as you keep forward, like going forward, what would be your process to adding more? Like once you have that?
Yeah, so as you iterate, just touching the parts of the code that you are changing. Or another approach would be to have end-to-end tests because, you know, like for example, when you use Cypress, because those tests are not tightly coupled
Cypress
to the code.
is really great, by the way, it really is.
Exactly, so because they're not tightly coupled to the code, right? You just like, you spin up a browser, you interact with a UI in a certain way, right? Those are going to be easier to write and they're going to provide a whole lot of value for a reasonable small amount of effort. So they're very efficient in terms of like a cost-benefit relationship.
Okay. 2 questions, one from Evgeny, one from Charles. They're very similar. What books would you recommend to read to achieve some understanding how to write testable code? And I mean not books that are written by developers for developers, but written by QA people for developers. Does it even exist?
Right, that's a good question because the books I've read are all written by developers for developers. And you've just excluded a whole range of possibilities, which I really like. But I think that it's important to have that QA mindset I've talked about, like trying to prove yourself wrong. And I think that if you read books about software testing in general, I think you can get a quite good QA mindset. And you know, by the way, I'm writing one specifically about tests, so you know, there goes the advertising.
That sounds great. That sounds great. Well, we're totally out of time. We don't have maybe just one more, and then we can wrap up. Have you used Puppeteer, and what was your experience with it?
No, I haven't used Puppeteer specifically.
Okay, so because it's something that came up as well. Well, I'm sure that you'll be available at the discussion zone as well. And you have to tell the story though. Shoes.
Shoes, right.
What's the story with the shoes?
Oh man, so I don't know, like they have fur, they're very comfortable, you know. It's like, another thing that's important is, you know, if you're nervous on stage, you know, because you're not wearing socks or anything, you can just take them off and you're like, oh yeah, it's so comfortable, you know, you can feel the earth, feel the energy of nature and you can just be, you know.
When is your birthday?
My birthday, 8th of May.
Okay, maybe I can send you some socks. Just for you to feel.
Christmas socks, please.
Christmas, obviously.
Okay, thank you.
All right, with this in mind, thank you so much for being with us, Lucas. Well done.
Thank you very much.
Yeah, thank you.